Journey away from the sun, past Earth and the inner planets, millions upon millions of miles. It's here that giants lurk, Jupiter and Saturn, spheres so cold and distant that the sun is no more than a tiny beacon in a vast twilight. These are the frigid outer reaches of the solar system, the edge of darkness.
It's a new uncharted territory out there. It's a new frontier at the edge of the solar system, and the next few years are going to probably bring many surprises.
Already, we've found gossamer rings around gargantuan planets. We've detected atmospheres on worlds that barely catch the light of day. We've spied a moon with a king-size crater, and other moons pocked with celestial buckshot. We've seen a planet-sized moon with an icy crust cracked like an eggshell. And beneath it, possibly an ocean warmed by volcanoes and supporting life. The outer reaches are weird and wonderful. Lakes of liquid methane on a moon that resembles early Earth in deep freeze. A moon that spews brimstone. Another that vents nitrogen. Exotic and eccentric moons. Moons, however rugged, that are mere slaves to their gigantic masters. Masters like Jupiter, a gas bag so big it could swallow every planet and moon of the solar system and still have room to spare. Farther out, Saturn and its spectacular rings, the show-off of the planets. Even farther, Uranus, with its tilted axis, the result of some ancient collision. And more distant still, Neptune, last of the four gas giants, ringed with rocky particles. But there's yet another planet that may not be a planet at all. Its crazy elliptical path occasionally takes it inside Neptune's orbit, a planetary joker.
Close in toward the sun are the terrestrial planets, the planets that are made of rocks and silicates, like the Earth. Further away are the gas giants, mostly made of hydrogen, a lot of water. And furthest away are the really weird things, the icy dwarfs, things like Pluto.
Pluto has a moon, Charon, half the size of the planet. They circle each other face to face as though joined by an invisible bar. A diminutive couple waltzing in a candle-lit ballroom.
Physically being on Pluto would be rather interesting. For one thing, the lighting levels are about 1,000th what they are on Earth. That means noonday sun would look like what the sun looks like now about 35 minutes after sunset. It'd be this kind of glow in the sky, and you could see stars in the daytime sky. There has been some controversy whether Pluto is a planet or some other object like a large comet or an asteroid. Well, certainly Pluto does meet all the criteria for being a planet. But the other interesting thing is that Pluto, in fact, may be the largest body of a collection of material, so-called the ice dwarfs, which in turn may be the parent material for comets themselves. This is the kind of material we've never seen before, and very, very intriguing because it may be some of the most primitive material in the solar system.
That's why NASA is planning a mission to Pluto. But timing is of the essence. As Pluto flies through space, its distance from the sun changes. At its farthest and coldest, the atmosphere freezes from gas to solid. The Pluto Express wants to get there while Pluto still has a gassy atmosphere. It's a 4 billion-mile trip, and NASA plans to use another planet as a kind of celestial slingshot.
Well, we're trying to launch before the year 2004, and that's to take advantage of Jupiter. But we can do a gravity assist on Jupiter, basically flying past Jupiter in order to push our trajectory toward Pluto. And this saves us flight time, and it also allows us to fly in a cheaper launch vehicle. Pluto expresses a much, much smaller spacecraft. It's about 1/10 the weight, smaller instruments, smaller radios, less power consumption. Everything is utilizing that technology. What we have learned in our explorations of the other planets with the spacecraft Voyager is that the one thing we can expect is we can expect to be surprised. And I think Pluto probably has a very, very high potential for surprises.
This desire to explore the outer worlds goes back decades. One of our most successful missions was Voyager, launched in 1977. Voyagers 1 and 2 have traveled billions of miles into space, and Voyager 2 is still sending back data.
The Voyagers were our first real close-up exploration of the outer solar system. They were designed as flyby missions, in other words, a quick look and detailed pictures of the outer planets, Jupiter, Saturn, Uranus, and Neptune.
It was a long journey to the outer planets. The Voyager twins used Jupiter's gravity to accelerate and redirect themselves. Saturn also was a stepping stone, but here the two craft parted company. Voyager 1 moved away from the solar system, while Voyager 2 traveled on to the remote outer planets. The Voyager twins carried many sensors. The most valuable of these were the TV cameras that in 1979 recorded the king of planets, Jupiter. Jupiter is surrounded by courtiers. 16 moons spin around in the Jovian kingdom. The Voyagers sent back images of moon shadows playing across the great planet's face. Voyager also witnessed firsthand the storms that raged in Jupiter's atmosphere. Angry clouds of gas in perpetual turmoil race around the equator. One storm is thousands of miles across, a huge swirling vortex of gas. It's the Great Red Spot. Two years later, the Voyagers presented us with our first good look at Saturn. It's been observed ever since we've looked into the skies. Its hallmark is its rings. The broad rings are actually thousands of individual ringlets, like grooves on a phonograph record. Different sized particles show up as different colors. Ice the size of peas make up the brown, while finer grains appear white. But the biggest fragments, about the size of a family car, make up the ring closest to the planet. Trillions of icy moonlets that glide around the planet's girth. Staring into space toward these rings from Saturn's cloud tops, everything seems serene. Nothing could be further from the truth. Saturn's storms are of epic proportions.
Just like our own planet Earth, Saturn is tilted over on its axis about 23 odd degrees. This means that it has distinct seasons as it travels around the Sun once every 30 years. And we have noticed that every Saturnian summer, a huge storm erupts from deep within Saturn, bursts onto the surface, and these storms probably would look like great blizzards of ammonia snow.
Life would perish in seconds here. Saturn's a typical gas giant with chemistry unlike anything on Earth. Voyager's pictures were just an appetizer. The upcoming Cassini mission should be a Saturnian feast, named after the Italian astronomer who studied the planet in the 17th century. Cassini will explore Saturn's entire system, rings, moons, and all. Professor Carolyn Porco, Lady of the Rings.
What we're hoping to learn from Cassini is how the solar system formed and how the planets formed, and we're going to examine the satellite system and in particular the rings. And we're also hoping to learn about what makes atmospheres tick and how stable they are, what brings about energetic jet streams like we have here on the Earth.
NASA isn't alone in this mission.
There are 17 countries involved in Cassini. There are something like over 3,000 people in the United States, 1,600 people in Europe, that are all pooling their energies to make Cassini a success. It's probably the last of the large unmanned robot spacecraft. We believe we've made Cassini a very reliable spacecraft. In fact, we think its failure rate, if you like, is actually less than that of the Voyager spacecraft, that it lasted so well.
The Voyagers will be a hard act to follow, but Cassini, with its superior instrumentation, has 2 decades of advances in technology on its side. The plan is to arrive at Saturn in the year 2004.
One of the main reasons for sending a spacecraft like Cassini back to Saturn some 25 years after Voyager had been there is to search for changes in the system. And so we would be delighted if we saw that the rings had changed over that period of time. That would give us information about the way they're evolving.
Many questions remain unanswered about Saturn, the most beautiful of the gas giants. Not just about its rings, but about the planet and its moons. Saturn's largest moon, Titan, is the source of most speculation.
Titan is the only satellite in the whole solar system that has a substantial atmosphere, and its atmosphere is believed to be similar to the atmosphere that we had here on Earth prior to the emergence of life.
Titan's orange hue comes from a primitive cocktail of gases. Here, methane snow falls through the nitrogen atmosphere. This is the same chemical duet that played on Earth in warmer climes and older times, 3.5 billion years ago. But on Titan, at -300 degrees Fahrenheit, the flint to kindle life was never struck. Cassini will send the probe down through the noxious atmosphere of Titan. Looking at this primitive, frozen Earth, it will be our telescope through time. For 2.5 hours, it will peer through the veil of Titan's atmosphere. Once landed, it will relay data and pictures, but just for a few minutes. Then, it will be claimed by either the cold or the chemistry of this hostile environment. That's all to come. Cassini won't arrive until the next millennium. Meanwhile, we can study Voyager images of other strange bodies that inhabit the Saturnian system. One of the spookiest is Mimas, another of Saturn's moons.
Mimas looks like a natural version of the Death Star in Star Wars because one of its surfaces is almost completely dominated by a giant crater. Now, had the object which caused the crater been slightly bigger, Mimas would have been totally destroyed and by now would have been assimilated into Saturn's rings.
Our knowledge of the solar system seems to come in bursts. Until 1781, Saturn was the edge of the solar system.
And then along comes William Herschel and discovers a brand new planet. Suddenly our world, our whole worldview, was much larger than it had been before. It was a significant step forward for understanding our universe, our place in our cosmos.
What Herschel found in 1781 was Uranus. For 200 years, all we could learn from our telescopes were the size, the tilt, and the composition of the planet. But with Voyager 2 in 1986, came the chance to get a close look at the planet. The first pictures were disappointing. Uranus was a bland, featureless world with little in the way of clouds. What Voyager did see was the rings. And they confirmed an amazing story. It's likely that Uranus was once blasted almost into oblivion. But before the planet became history, a residual core had enough gravity to pull most of the pieces back together into the planet we see today. Its outer rings are the evidence of that cataclysmic event. Voyager surpassed itself when imaging Miranda, one of Uranus's 15 moons, flexing and moving. Instead of a few pages, Voyager wrote whole chapters about Uranus and its moons. Then, the Hubble Space Telescope took up the story.
When the Hubble went back and had another look at Uranus, there was an increasing amount of cloud activity, possibly due to changing climate conditions as Uranus goes through different seasonal changes, which should be monitored by the Hubble over the next 20 or 30 years.
As we struggled to look further into space, observation gave way to calculation. A new planet was predicted before it was actually observed. Uranus kept changing speed, suggesting that something big was pulling on it. It was Neptune, predicted before it was seen by a German telescope in 1846. On the last leg of its odyssey, Voyager flew past the Neptune system. The date was August 24th, 1989. Voyager confirmed the existence of yet another ring system. Its images allowed us to paint this picture. The craft came within just 3,000 miles of the cloud tops, its closest planetary encounter.
Voyager revealed marvelous, dynamical systems of bright clouds, dark clouds, bands, belts, all sorts of very interesting cloud structure on the planet.
Those expecting a dull, frozen planet were in for a surprise. Neptune was alive with colorful weather systems, winds raging at over 1,000 miles an hour, storms that appeared as vast blue spots, one of them larger than the Earth. But 5 years later, Voyager's great storm had gone. In 1994, Hubble found a new one, but in the northern hemisphere. Neptune's moon, Triton. It orbits the planet in the opposite direction of most moons in our solar system. This suggests Triton is an orphan captured and adopted by Neptune, an odd couple, a blue gassy giant, and a frozen icy moon. Voyager saw the coldest body in the solar system, Triton, a moon at minus 400 degrees Fahrenheit. Here, ice is as hard as steel. The lines, hundreds of miles long and about 10 miles wide, are collapsed ditches. Smooth areas, possibly frozen lakes. And there are few craters, evidence of a young exterior being actively renewed. The black streaks come from the moon's strangest features, its geysers.
What we seem to be looking at here are geysers, some kind of gas, probably nitrogen, being shot up to about 6 miles high, and then being blown at a 90-degree angle and then traveled many hundreds of miles, if you like, downwind.
Dust falling from these jets form the strange black trails across the surface. This was the last body in our solar system seen by Voyager. It gave us wonderful glimpses of faraway places.
The Voyagers were probably the most successful spacecraft ever constructed and built. Now, they weren't without their problems, but they did their job. But their job was merely to quickly fly past each planet, take a few snaps, and send the pictures back. They were designed to pave the way for the spacecraft that were going to visit each planet and stay there, become a natural satellite, go into orbit around the planet, just like Galileo.
This craft was to be part of NASA's next generation of explorers. Designed in the 70s, built in the 80s, it would pay homage to the largest planet.
Jupiter is just a fantastically interesting, dynamic place, an entire miniature solar system.
Jupiter, we think, is important, specifically because we think it contains some of the same material that made up the original solar nebula from which all the planets in the sun formed. So if we can measure what the composition of Jupiter is, we think what we're measuring is what the solar system was originally made of. And that's a fundamental piece of information. Galileo will provide extended coverage of how the atmosphere is changing, what goes on in the magnetosphere over time, and allow us to come back very close to each one of the satellites.
Throughout the 70s, scientists at the Jet Propulsion Laboratory were designing the most ambitious exploration of the Jovian system. Galileo would ride on a powerful liquid-fueled rocket, the Centaur booster, on a fast trip to Jupiter. Both Galileo and Centaur were to be lifted by the space shuttle into Earth orbit. From there, the Centaur would take over. But on the launch date in the early 80s, neither the Centaur nor the shuttle were ready. The bright, optimistic days of Galileo's early construction were eclipsed by setbacks. Eventually, both Centaur booster and shuttle were finished. May 1986 was set for Galileo's launch. Just 4 months beforehand, hope turned to despair. In January 1986, tragedy befell the Challenger. The shuttle program was put on hold, and silence fell on the Kennedy launch pads. Liquid-fueled rockets were banned from the shuttle's cargo bay, and so Galileo's Centaur booster had to be abandoned. Galileo waited for the shuttle. It spent the next 3 years being modified, shunted across the country, and put into storage. Finally, in October 1989, the day came.
We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
The spacecraft is a part of us. It's the extension of us. And maybe it's true that the nerve endings are not at the spacecraft, but our emotions are on that spacecraft. Absolutely.
TV1, Houston. Time, Houston. The spacecraft is stable. Galileo is on its way to another world.
Roger, Atlantis, we copy. That's great news. Thanks.
6 days after launch, Galileo and shuttle parted company. But with no powerful Centaur to take Galileo directly to Jupiter, a roundabout path was needed. Galileo would swing by planets and asteroids, picking up speed and direction with each encounter, winding itself up for the final slingshot. Instead of the original 2.5-year trip, Galileo would take 6 years to reach Jupiter. But NASA took advantage of these flybys. The surface chemistry of the dark side of the moon was compared to the light side. Galileo also took atmospheric measurements of the ozone levels over Antarctica. But things were going wrong again. Just as the craft was leaving Earth for the final time, the high-gain antenna refused to open properly. The awful truth dawned on NASA. With the antenna stuck, Galileo was virtually useless.
The high-gain antenna was really its primary communication tool with the Earth, which of course is hundreds of millions of miles away. And it was designed as a huge dish to send back huge amounts of data. And when the fault developed in the antenna, the great umbrella got stuck and couldn't open.
For things which we think that there's some reasonable prospect might not go as we expect, we develop contingency plans. We developed no contingency plans for the high-gain antenna not opening because we were very confident that it would.
They ran all the motors backwards and forwards. They created hammering motions. They spun the spacecraft one way or another. They heated it, they cooled it, they pushed it, they pulled it. But there it was, floating in space, shooting out to the planets. What can you do?
We've done just about everything we can. We've built a very robust sequence. The spacecraft has been designed for that extremely hostile environment that it's going to go into. And there's not much else we can do but sit back and worry at the moment.
But it never did open properly. All of those years of storage, all of those journeys across the U.S. had taken their toll. Now, instead of sending back a picture every few minutes, Galileo would trickle out only enough data for one picture every week. But what is it about Jupiter, this huge ball of gas, that attracts all this interest?
Jupiter's big. There's no place to stand.
Tremendous jet streams in the atmosphere, satellites circling it, a magnetic field whipping around every 10 hours.
Has a huge feature, the Great Red Spot, which is always intriguing.
And the storms last for hundreds of years.
The Great Red Spot, a storm large enough to swallow the Earth 3 times over. It was all that most people knew of Jupiter until 1994, when the world watched 21 pieces of comet Shoemaker-Levy explode in its atmosphere. They were fragments of a comet torn apart by a close scrape with a giant planet 2 years earlier. Jupiter pulled the fragments into its clouds. These fragments disintegrated in huge explosions in the upper atmosphere. Afterward, Jupiter wore a few black eyes. Some expanded to the size of our planet. Explosions like this would devastate life on Earth. For Jupiter, they were no more than a bee sting. At the time of the Shoemaker-Levy impacts, the Galileo spacecraft was well on its way to Jupiter. Since Galileo's launch, computing power had mushroomed. Engineers could now compensate for the flawed antenna with a technique that compressed data received from the spacecraft, allowing pictures to be sent in hours rather than days.
You're welcome.
Some impact pictures trickled back to Earth. But just as it seemed Galileo was recovering, another calamity stopped the hearts of the engineers. The tape recorder appeared to fail. Galileo was just 2 months away from its rendezvous with Jupiter.
That was, to me, the worst of all, because at the moment when it happened, I was sure that it was broken. A lot of people were convinced that it had broken, and there was no recovery.
The tape recorder's main duty was to record data, information from the various sensors and the camera, and send it back to Earth at the appropriate times. When the main antenna was proven to be faulty, the tape recorder assumed a much greater importance.
They eventually discovered one end of the tape was faulty. By ordering the onboard computers to ignore that portion, the rest could be used to record pictures and data. But there was a price to pay. Galileo's route was planned so it would encounter Io, a cauldron of sulfur volcanoes and one of Jupiter's most intriguing moons. But the fault with the recorder forced a shutdown of the cameras. Galileo flew blind past the moon. Galileo seemed jinxed. An expensive trek to the Jovian system was being dogged by failure. Galileo was actually two craft. Some months earlier, a probe had been sent from the main craft. The main craft would go into orbit around Jupiter, while the probe would plunge into the Jovian atmosphere. It was on a one-way trip to vaporization. December 1995, and the probe's about to have its 60 minutes of glory, zipping as much information as it can back to the orbiter before being fried.
The probe entry into the atmosphere is the most difficult planetary entry that we've ever attempted. The probe will hit the atmosphere at 106,000 miles an hour. That would take us from the west coast of the United States to the east coast in under 2 minutes.
Hurtling down toward the planet, could the probe endure such a drastic deceleration? Crashing into the Jupiter atmosphere at that speed would resemble this kind of impact. Would the craft survive? Would the sensors operate? Would the data get back to the orbiter?
I am coming to Judgment Day. That Thursday, the 7th of December, for me was Judgment Day. The next day, I was going to be in heaven or hell. There was no two ways about it.
From 500 million miles away, to these, our most sensitive ears, would come Galileo's electric whispers. These dishes were to listen for the signals from Galileo as its atmospheric probe underwent its hour of judgment. Scientists here would be the first to know its fate. Goldstone Tracking Station focused, listened, and waited as the hour for the probe's entry drew near. December 7th, 1995, and Galileo's ambitious foray to Jupiter is attracting worldwide attention. Print reporters are here. So is TV. In the conference room, scientists from all over America come together to learn the fate of the mission. With Galileo's track record, the prospects aren't good.
We're just about ready to begin.
The world is listening to JPL. JPL itself is online to Galileo Control to hear the probe's fate.
Systems, this is Probe.
Go ahead, Probe.
We want to verify that the orbiter has successfully locked onto a signal from the probe.
That's it? Is that it?
The atmospheric probe was transmitting. Things were looking up.
Oh, this is stunning. This is a testimony to the ingenuity of the brilliant scientists and engineers that have worked on this program. They went through the perils of Pauline, of losing a launch vehicle, of losing the high-gain antenna, having a problem with a tape recorder, but they did it anyhow.
The little probe made the most spectacular kamikaze dive in history. In under a minute, the atmospheric drag reduces its speed by 40,000 miles per hour. Its heat shield sears at 21,000 degrees Fahrenheit. Another minute, the parachute is deployed. The speed is down to 19,000 miles per hour. Another 10 seconds and the protective cocoon is jettisoned. The instruments are directly exposed to the Jovian atmosphere. At 4 minutes in, the probe reaches the visible cloud tops. For the next 90 miles, unimaginable extremes. Freezing cold, severe winds, increasing temperature, and pressure and turbulence unknown on Earth. The plunge is all over in 57 minutes. Like an ice cube in a furnace, it melts. The scientists are elated.
What we learned today was that the probe survived entry, and data is on board the orbiter to tell us about Jupiter, data we've never collected before.
The probe measured the winds, measured the chemical constituent, measured water, searched for lightning, and measured the amount of light as the probe descended into the atmosphere.
And we found that the winds, which at high altitude on Jupiter are very, very strong, 300 miles an hour, those winds don't die off as you get deep in the atmosphere. They, in fact, get a little stronger, if anything. That's one of the things that tells you, is that the atmosphere of Jupiter is being driven from its fundamental energy sources by energy from within Jupiter, not just from absorbed solar energy at the very top skin of the atmosphere.
We expected that water would be the third most abundant molecule in the atmosphere after hydrogen and helium. In fact, the probe found about 5 times less water than we expected. And that could either be because Jupiter's a dry planet or because the probe hit a dry spot. But then, of course, the question is, why should that dry spot persist in spite of all the mixing and activity that's going on in the atmosphere? We're still arguing about that one.
But far more is to come. The Galileo spacecraft will slot into orbit around Jupiter, aligning itself for the main part of its mission.
The Galileo spacecraft can be directed by the information, particularly the images that amateurs and professional astronomers have gathered over a long time.
We send reports on our observations to Dr. Glenn Orton at JPL for liaison with the Galileo team. The advantage of Jupiter for amateurs is that the really important characteristic features are big enough to be seen with an amateur telescope. So one can see, for instance, dark spots in the equatorial region, and it was one of those that the Galileo probe went into, and we were able to follow that dark spot for several months before Galileo arrived. So we can give them information that they may actually find useful in planning spacecraft activities.
John is a particularly good amateur astronomer in the sense that he helps us collect data from other people as well. So John serves as a conduit, particularly among British amateurs, but also on an international scale. One of the ways in which we get the information from John is through the internet, and that's actually very good for us. We can use it almost immediately and see it almost immediately.
No Earth-bound telescope could get pictures as good as these. The Great Red Spot, as seen by Galileo. High-resolution images give this astoundingly detailed view of the long-lived storm system. Galileo searched the upper atmosphere for any signs of the Shoemaker-Levy impact, but all traces had vanished. Perhaps the evidence was swept away in the turbulent atmosphere, the swirling storms and cyclones of frozen ammonia, more proof from Galileo of a dynamic atmosphere. Encircling Jupiter are very faint rings. Invisible from Earth, they're overwhelmed by the light of Jupiter. It's like trying to see a candle against the beam of a searchlight, but they could only be glimpsed if you were hovering near the clouds. The best time to view them is when they are backlit by the sun. The one major ring measures a few thousand miles across and seems to be made from trillions of tiny dust grains, as fine as cigarette smoke. Particles from constant collisions are thought to keep the ring replenished. Galileo captured Jupiter's rings, but the spacecraft has other appointments to keep. December 1995. Galileo is flung out 12 million miles, but Jupiter's gravity pulls it back and then guides it on the tour through the moons. With each new orbit, the craft would offer new insights.
The Voyager explorations in 1979 showed us remarkably that each one of these moons had its own character. They very quickly became like sort of old friends to those of us studying them. Each one had a different face, looked like it had gone through a different history, been beat up in different ways.
And we're going to want to see what those things look like when Galileo flies 350 times closer than the Voyagers did.
The pictures Galileo sent back were worth the wait. Images of moons never before seen in close-up.
Callisto is the most distant of Jupiter's moons. It's also got probably the most cratered and the most ancient surface in all of the solar system. Just one look at Callisto and all you see are craters. Craters from tiny pits to things like this, 10, 20, 30, 50 miles across. This is the center of a huge impact that would have occurred eons ago. It radiates outwards in concentric rings out to a diameter of about 1,000 miles.
Galileo saw how Callisto was paying a penalty for being so close to Jupiter. The gassy sphere, with its powerful gravity, sucks in any passing comet or asteroid that strays too close. Callisto is often in the way. In contrast, Europa showed a face completely unlike Callisto's. Europa's lack of craters suggests a young surface made up of fresh material. Cracks seem to show where the moon's crust shifted, allowing liquids to well up from below.
The most intriguing thing about Europa are the series of thousands of lines that crisscross its surface, rather like a whole highway system. From the shots of Voyager and from far away in Galileo, these lines appeared single. When you look at them in close-up, say through the more detailed pictures of Galileo, we see them as double. Now, the reason for this seems to be that we're looking at a place where water or a liquid has come up through a crack in the surface, flowed outwards, and re-solidified or frozen. And what we're looking at is probably a kind of a levee. And the levees, or the cracks, are in the order of 400 to 500 feet across.
Europa may hold our solar system's biggest surprise: life. Not on its surface, but 60 miles beneath. As on Earth, there may be warm oceans with volcanic vents where creatures cluster around, feeding on the nutrients. Surely the next spacecraft to Europa should carry a tiny robotic submarine. Sandwiched between Europa and Jupiter is Io, unique in the solar system, for at its heart is hot, molten sulfur that feeds volcanoes, very strange in this icy realm of frozen gases. Io, where black sulfur marks volcanic vents. Red ash surrounds them and yellow brimstone lava flows in the valleys. A beautiful colored patchwork, but there's always a dynamic volcano to be found.
The most obvious manifestation of the volcanism that we see are the active volcanic plumes that we see best against black sky and the bright limb.
At least one of Io's volcanoes seems to have trouble keeping put.
Prometheus is an active volcanic plume that we saw during Voyager, and very recently from the Galileo images we saw that, lo and behold, Prometheus is still active. It looks roughly the same, only we were surprised to look and notice that it wasn't quite at the same place. It's actually migrated about 75 miles to the west of its previous location. And this is very unusual. On Earth, volcanoes don't move around like this, but on Io, apparently they do.
Fountains of sulfur. A plume shoots 150 miles into the sky. A flight over Io would be a magnificent experience.
The way in which the active volcanic eruptions respond to the Ionian environment, and that they're very large, that's because of the virtual absence of an atmosphere as well as the lower gravity on Io, so they look very different.
With no wind to blow the red ash away, it falls in neat rings around the black vent. This volcanic activity is driven by heat from a strange source.
The reason why Io is so volcanically active is because of tidal heating from Jupiter and also from the periodic tugs of Europa and Ganymede, the next two satellites outward from Io. And these bodies together perform a gigantic tug of war. And just as when you bend a piece of metal back and forth, it gets hot, Io is being stretched back and forth and getting hot.
Io, the only body in the entire solar system, apart from Earth, to be volcanically active.
Io is a fascinating experiment in planetary chemistry and physics, where we take a planet, essentially, and heat it intensely and watch what happens.
For the little spacecraft that could, there is no rest. Galileo goes on to Ganymede. Over 3,000 miles in diameter, this is the largest moon in the solar system. It's a mixture of ice and rock. Galileo made a number of passes, and at its closest, the craft came within just 200 miles of Ganymede's frozen surface.
This is a Galileo close-up of the moon Ganymede. It's dominated by a fresh, young crater just a couple of miles across, and we can see to this side of it a dark area of material that was thrown up whenever the crater was formed by an impact some time ago. But overall, this picture is rather intriguing because it kind of looks like a close-up of, let's say, an elephant skin. It looks as if it has been pushed and pulled and wrinkled. And that's what we think has happened to the surface of Ganymede. It has been pushed and pulled and wrinkled by forces that we would think of as being ice quakes.
Ice quakes? Galileo returned surprising images of fault lines as it scanned Ganymede's heavily disrupted surface. It's a surface furrowed into a crisscross of ridges and troughs. The whole of the moon appears to be ice blocks that constantly slide and shift past each other.
One of the close-up images of Ganymede from Galileo revealed a rather beautiful line of craters running right across the surface. Now, this was probably caused by a rain of cometary debris, rather like the impact of Shoemaker-Levy 9 on Jupiter.
By tracking Galileo precisely as it flew past the moon, scientists made a remarkable discovery. Ganymede had properties that made it more like a planet than a moon.
As Galileo flew past Ganymede, it detected signs of a magnetic field. This is most unusual, a magnetic field inside the magnetosphere of the giant planet Jupiter. The magnetic field tells us something about what goes on inside the core of a planet, or in this case, the moon.
These results have allowed scientists to build a picture of the internal structure of the moon. Beneath a thin crust is an icy shell about 500 miles thick. Under that is a molten rocky mantle. At the heart is a dense metallic core. Together, the core and the spinning mantle produce a magnetic field. The soaring whistles and static in one of Galileo's sensors were the telltale signals of the magnetic field. Galileo signing off for the time being. So far, the Galileo story contains chapters of astonishment, disappointment, and elation.
The pictures that Galileo has returned have been excellent. I mean, in terms of quality, they have been every bit as good as we all had hoped. And what we haven't got is the quantity, but it's quality that counts.
Despite a number of setbacks on the Galileo spacecraft, the high-gain antenna failing to open up, a filter wheel getting stuck on one of the instruments, another instrument failing at certain points when it's too close to the planet and gets hit by radiation. It's like riding along with the little engine that could. Despite a number of setbacks, we're still chugging along and getting over that hill onto the other side of the mountain.
Galileo will carry on, using its thrusters and gravity to maneuver itself past planet and moons. Although it won't tell us everything we want to know about the Jovian system, each new piece of data will help us paint a clear picture of Jupiter's realm. Because space holds as many questions as it does stars, we will continue to send out explorers. It's in our nature to inquire how the universe came to be. With each outward step, we come a little closer to comprehension. While we may not learn the answers in our own lifetime, we lay the foundations of understanding for generations to come.
We should be thinking in the long term, and in exploring the Saturn system or any of the other planets in our solar system, what we're doing is we're gathering information. We're filling the libraries on Earth with information about our celestial neighborhood.
Some questions still remain. We don't yet know what the colors of Jupiter are made from. What are the materials there? There are still questions about Jupiter that will want us to go back.
Some explorers we send into the depths of space may, like the Voyager missions, have a second task. With each passing day, the Voyagers move almost 1 million miles farther away from home. The craft bear the signature of their creators, in the hope that one day another form of intelligence will find them. An inscription tells of life on our small blue planet. The Voyagers also carry the sounds of human life, hellos in 60 languages, and music, Mozart's Magic Flute and Chuck Berry's Johnny Be Good.